first, I would like to thank David and Xiaomin for having me here. From the talk, from the title, you see that it's not deep learning. Okay, clearly it's not deep learning, and but they still would like to have me here. And you'll see that later in this talk. And this talk is essentially on non-convex optimization by first-order method, and which is a very hard topic in deep learning. So it's kind of related. An EM algorithm is, of course, independent interest in our field in statistics. And EM algorithm is one of the most celebrated algorithms in our field, and the arrangement paper, and is I believe it's the most cited paper still. But in literature, and there are few results, and to understand EM and statistical and computational guarantees. So this is a joint work with Yihong Wu. And some of you may know that, and the Department of Statistics at Yale was just recently expanded to Department of Statistics and Data Science. And the faculty size has already doubled, and it's going to triple very soon. And so now, I'm kicked out from the old building, 24 Hill House, and now I'm in 10 Hill House. My office is about half size of the original one. And Yihong and I are next to each other, and our offices are next to each other, and that's why we started to collaborate. And he's very talented. He was just promoted to associate professor, and I believe we are going to promote him to full professor in 2 years. Okay, so EM algorithm is an algorithm to approximate MLE. And we have, we have observation Y, write down the log likelihood, and try to maximize it. Okay, that's what we do, in statistics. And when we have a latent variable, and the log likelihood, and it could be very messy, highly non-convex, if I use the phrase from Xiaomin, highly non-convex, and computationally intractable. So EM algorithm is an algorithm to approximate an MLE. An EM algorithm is an iterative algorithm. And for each iteration, there are 2 steps. One is E step, and the other one is M step. And in the E step, we define a function Q. And the function Q is a weighted average of complete log likelihood. And the weight is given by the conditional probability of your latent variable. And then, in the M step, we maximize the Q function. So by the definition of the maximizer, we know that the right-hand side of the equation is more than or equal to 0, right? It's non-negative. And the justification of EM algorithm we learn from any textbook or Wikipedia is this. And it turns out the marginal log likelihood also increases. And it increases at least the same amount as the Q function increase. So the log likelihood is increasing. But that doesn't mean it's going to converge to global minimum, even to MLE, right? And it just means, you may converge to a local minimum, and you may get trapped in the side point. So in the past 2 years, we spent a lot of time trying to understand EM. But the progress we made, you see that it's very limited. And in this talk, I will consider a Gaussian mixture with 2 symmetric components, minus theta star and theta star, with equal probability, half-half. Very simple model. And a useless model, and for any real-world application. And the sign of the theta star is not identifiable. If you multiply every observation yi over here by -1, you get the same distribution, right? is symmetric. Okay. So, and the sum of theta star is not identifiable, and that's why it's kind of natural to consider this loss. And the norm over here is the Euclidean norm, L2 norm. Okay, and for and if we we want to estimate the theta, and the upper rate of convergence is d over n to the power 1/4. And some of you may get confused. Hey, Harry, that must be wrong. I have very nice and likelihood over here, very smooth, and we should expect square root of d over n rate, right? That's the classical MLE theory would tell us. But the problem over here is this. The phase information could be degenerate. When theta star is equal to 0, what's the phase information there? It's just 0. So I remember a few years ago, I give this problem as a qualifying exam problem at Yale, but only for d equal to 1 case. So, and because the phase information is degenerate, and the upper rate for estimation is d over n to the power 1/4. Okay. And for this problem, the EM has a very nice form and a beautiful form. Okay, and the EM update is is a weighted average of yi, and the weight is given by a tangent hyperbolic function. And the tangent hyperbolic function, and some of you may not remember, and that's why I put a remark over here. And it's a function between -1 and 1. And if we know the oracle and of the sun, and of the latent variable. Okay, if you know the latent variable 1 or -1, then you know what kind of weight you should put over there, right? On 1 or -1. If you know the sum of the corresponding mean, you know what to do. And the tangent hyperbolic function over here is just try to mimic the oracle. It's a number between -1 and 1. Okay, when n goes to infinity, and we have the population version. Okay, and for the population version, and the analysis usually is much easier because it's all deterministic, right? It's just deterministic analysis, and so it's but it's helpful to know the population version, and if we know the population version well, and then it's helpful for us to understand the sample version. Okay. At the very beginning of the talk, I mentioned, and this is essentially a non-convex optimization by first order method, and this is the reason. And this is a very simple fact. It turns out an EM update in this problem is gradient descent with a fixed step size. Okay, in machine learning they call it learning rate, fixed learning rate. And this is a very simple fact, but it's a very useful fact. And I'm going to use this fact later in my talk. Any question? And there are some very interesting and recent progress to understand this EM problem. For this EM problem, and those authors show that from Berkeley. And if two centers are far away from each other, that's the theta star, L2 normal theta star, are far away from each other. And if the initializer is close and to the truth, and then the shell and EM converges. Okay? And that's an interesting result, but we may have questions, right, after you see this kind of result. Is it really necessary to have two centers far away from each other? That's one question. Another question is, do we really need such a warm initialization and very close and to the truth, very close to the truth? And 2 years later, and these authors show that, and if you consider the population version, okay, n is infinite, and in that case, it's easier analysis. Everything is deterministic. Then they show that, and an EM converges globally, as long as the initializer, theta 0, is not orthogonal to the truth and theta star. So, and that's a very interesting result, very, very interesting result. But understanding the sample version is very different, is far more challenging. And these three people are from MIT and very good and theoretical computer scientists. And they show that, and okay, they analyze the sample version. And but they have to do sample splitting. And for each iteration, EM iteration, they have to use a new sample. So they split the sample into many, many pieces. Every time they use a new sample. And now you see the reason, right? Your output is dependent with your data. And that dependence is very hard to analyze. That's why it's very hard to analyze iterative algorithms. And so they avoid that by creating independent sample. And also, and for each iteration, they change the EM algorithm a little bit by some kind of renormalization and restart. Okay, I'm not going to talk about that. So, and what Yihong and I have been trying to do is this. And can we be very faithful to the EM algorithm? Okay, and no sample splitting, and for finite sample, and also, okay, and can we get rid of the separation condition? As far as I know, and we did some simulation, when theta star is equal to 0, the EM still converges. And can we get rid of the warm initialization condition? Okay, this is the first encouraging result for us, but only for one dimensional case. And this is the result. And we show that, okay, and for one dimensional case, we show that you could start from anywhere, or for EM algorithm, you could start from anywhere as long as the initializer is not equal to 0. And we show that EM converges after at most square root of n times log n steps. And after at most square root of n times log n steps, and you see that and the output is very close to the truth, and the rate over here and is optimal. And from the number of iterations, you see that why I do not like sample splitting. Suppose I have to iterate square root of n steps. If I do sample splitting, then every sample would be like square root of n. So too small. You are losing a lot. So here's the proof. And the proof actually is very simple. And because it's too simple, we got the result like 2 years ago, but we never published it. And okay, and what we did was to compare the sample version and the population version. And for population version, we know that it converges to theta star. So, and the solid blue line, the solid blue curve, it corresponds to the population version update. And the right line is a 45-degree line. And the intersection is the theta star. That's the fixed point and for the population version update. So if you update and then converge to theta star, okay, that's the population version, that's the truth. So, and then you see on the two dashed curves. And these are just upper and lower bounds, and between upper and lower bounds, and to sandwich my sample version. And of course, it's centered around the population version. And okay, and the upper dashed line and gives an upper bound. The fixed point is the upper bound. The lower dashed line and the fixed point and is a lower bound for my sample version update. So the difference between theta plus and theta minus and gives the accuracy of estimation. And that is this guy, okay? And some simple analysis, you will show that the difference between theta plus and theta minus is this guy. So let's say one dimensional case. Yes? Oh, and when t is sufficiently large, and what I mean is t is more than equal to square root of n times log n. Yeah. That's a good catch. Yeah. But this analysis cannot be extended to d-dimensional case when d is very large, like this, as large as the sample size. And the reason is this. And for one-dimensional case, you see that and the perturbation is like 1 over square root of n, right? And let's factor 1 over square root of n. When it's d-dimensional, and if you have done any theoretical statistics, you will know that, and the factor becomes square root of d over square root of n. And when d is big, okay, and the whole analysis is destroyed, and we are completely screwed up, and so we cannot really do anything when d is high. But this one-dimensional analysis and gives us hope, and that's why we could keep working on it for 2 years. Any question? Okay. And for the d-dimensional case, the output and we get is d-dimensional, and the output could be highly dependent with your data. And when let's decompose our output into 2 parts. One is projection to theta star. That's the signal part. And the other one is orthogonal to theta star. And what we want to show is this. And the orthogonal part goes to 0, of course, right? That's what we want to show, and goes to 0. And when d is equal to 1, and one-dimensional case, we do not have the orthogonal part. That's exactly equal to 0. Okay. And when d is more than equal to 2, this guy is no longer equal to 0. We are hoping to show this guy goes to 0. And okay, for the signal part, and we hope we could show an alpha t and converge to the L2 norm of theta star. Right, that's the signal part. And okay, due to the rotation invariance, and we are going to assume, and for our data, y1 to yn, only the first coordinate has a signal, and the rest has a distribution normal 0, 1. Because we are taking invariance, so I'm not losing anything. Okay, and then correspondingly, and the projection to theta star is just the first coordinate of my output, and the beta t corresponds to the magnitude of the rest of coordinates. And we are going to show the beta t goes to 0, and alpha t converges to the L2 norm of theta star. Okay, is that clear? Okay. So this is our result. And this is the main result. The main result is this. And you could randomly pick an initializer from unit sphere. Okay. Or you could just pick one of the observations as your initializer. And as long as the dimension of your data is less than the sample size up to a log factor. And then we show that after at most and square root of n times log n steps, and EM converges. And converges and this is rate optimal up to a constant factor. So when you start and the theta 0 is nearly orthogonal to theta star, right? And because we randomly pick a theta 0 from the unit sphere. And it's more than that. And we could even show that. And if you indeed have some signal, that means the signal sequence is bigger than the estimation accuracy. That's d over n to the power 1/4. And then the EM output is not only rate optimal, but also attending the rate constant. It's mimicking the classical MLE theory. And that's what you get from the classical MLE theory. So okay, and these are two very important points. And one is we do not really need a warm initialization. A random start would be sufficient. One random start would be sufficient. And we do not need to do some splitting. And in addition, we do not need any separation condition. of between two centers. D of n to the power 1/4. That's the optimal rate. Yeah. It's not published yet, and we are trying to write it up. It's just too long. For a very simple model, I guess the proofs has already 70 pages. So, okay. Any question? Oh, high probability is, yeah, we have is 1 minus n to the power minus 3. Yeah. Okay, here's the proof. Yeah. Oh, okay. Okay, and it's better to explain it from one-dimensional case. One-dimensional case, and you have half normal theta 1 plus half normal minus theta 1, right? And if you calculate the Kullback-Leibler divergence between this one and normal 0, 1, then you get n times theta to the power 4. And then that gives the rate n to the power minus 1/4. And yeah, that was the qualified exam problem they gave. That comes to point argument. Okay, so here's the proof. And the proof has 3 stages. And the most difficult one is the first stage. And when we start, and the theta 0 is nearly orthogonal to theta star. And we want to show that after some iterations, and the angle is slightly better than 90 degrees. I mean, slightly smaller than 90 degrees. After is smaller than 90 degrees, and there are many ways to do it. And now the analysis is becoming, now we have, have some signal over there, and then it's becoming easier. And then, I could just use the analysis I used for the one-dimensional case to compare the sample version and population version to use a very crude empirical process bound, and it will be sufficient. And for the second stage. So second stage is more or less routine, and after you know the one-dimensional case. And the most difficult one is the stage 1. How do you go from 90 degrees to slightly better than 90 degrees? And the third stage is even simpler, but it's most interesting. And as a statistician, and what you get is not just optimal rate, but also the optimal constant, mimicking the classical MLE theory. And the proof reminds me a recent trip to Leiden in Netherlands in honor of Art van der Waard. And and I started, I could fly to Europe either from China or from US. Then at the very beginning, what's the angle? That's 90 degrees, right? Yeah. And then after I fly to Europe, I believe I fly to Copenhagen, and from Copenhagen to Amsterdam. And then that's the second one. There are many ways to do it. It's relatively easy. And you could by train or by flight or even drive. And the last one, you couldn't really see it. That's from Amsterdam to Leiden. And have you ever been to Leiden? It's a beautiful city, really, really beautiful. And I took a Uber ride from Amsterdam to Leiden, and it's really beautiful. And to see around, so you cannot really see it over here, and it's basically one dot. So that's the third stage of the analysis. Okay, now the first stage. The first stage, and we have output, theta t. The theta t has 2 components, and one is projection to theta star. That's our signal part. And the other one is orthogonal to theta star. That's the noise part, basically. And for the noise part, beta t, it's very easy to show, just decrease to 0. But decrease kind of slowly. And the analysis of alpha t and beta t are entangled. And that makes it extremely hard to analyze alpha t. And And for the alpha t plus 1, I could write it as alpha t and times 1 plus L2 normal theta star. And then, okay, then they have a little negligible part. For that negligible part, if you use empirical process, a simple empirical process, and to prove it, then you have square root d factor, then we are screwed up, and we cannot prove the signal is increasing. We cannot prove it. So we have to be extremely delicate analysis over there. So, okay, here's the idea. Okay, and the idea, that's the very important idea, and I learned from the workshop organized by Xiaomin. And Professor Jian Qingfang gave a talk and to introduce the sign perturbation idea. Okay, the sign perturbation idea, what's this idea? Okay, we have our data, y1 to yn. Okay, our signal only appears in the first coordinate, which means L2 norm theta star or minus L2 norm theta star with equal probability. And now we create a fake data. How do we create? Okay, I'm not really creating it. I'm just in my analysis I need it. I multiply the first coordinate by random marker, -1 plus 1 with half probability. Okay, the distribution of my y tilde and y are identical, right? By the definition, they're identical. So and from the y tilde, I could run my EM. I get an output theta tilde. And the theta tilde and the theta hat have the same distribution, right? Because one is from y tilde, one is from y. And the theta hat is from the original data. They're supposed to be very close. The good thing now is this, very, very important. My theta tilde is independent of the sign of the first coordinate of my data, because by construction over here, it's independent of that. It's more importantly, the sign of the first coordinate is not only independent of theta tilde, it's also independent of the magnitude of my first coordinate. It's also independent of the rest of coordinates, right? And the sign, RID, is one-dimensional. In this way, we reduce a d-dimensional dependence to a one-dimensional dependence. That's the way we succeeded. That's the key idea, and we learned and from this paper. And Soma is also in the audience. And the intuition for this success is this: at the very beginning, you iterate, and your output is nearly orthogonal to your truth. You do not really, your output is nearly independent of your data, right? How do we exploit that? And this is the way to exploit the intuition. Okay, and after the first stage, okay, that's the most difficult stage. And then, our signal, we have some signal. Actually, and our signal is somewhere over here. It's on the right side of theta 0, okay? And that's our output from the first stage. And if you cover, if you cover the left-hand side, only look at the right-hand side, if you look at the plot, and the plot is nearly identical to one-dimensional case, right? See, we have the population origin, we have the lower bound, and we have the upper bound, and we have two fixed points, and the difference of the two fixed points gives the accuracy. And the accuracy is d over n to the power 1/4 up to log factor here. That's the second stage of the proof. And the second stage of proof is very routine, and basically just using some basic empirical process and some unit bounds. Okay, any question? No, that's just for notation convenience, and yeah.
In general, just perturb the first two coordinates without looking at the remaining coordinate, and also
No. And what I meant is this, you just look at one, you just perturb the direction and of theta star. That's what I meant. Yeah. How many minutes do I have? 10 minutes. Okay. And okay, after the second stage, and we move to the third stage, and that's a very interesting stage. And that's a stage, and I guess a theoretical computer scientist would not think of. After we are in a very close neighborhood of theta star from the second stage, and what shall we do now? And if you talk to Peter Binkel, and he will know what to do. He will say that, okay, I just want one step Newton-Raphson. Okay, that's in his celebrated paper, one step and a Hubbard estimate. You just run one step and Newton-Raphson, and then the estimator is not only rate optimal, but also attaining the right constant. And of course, I cannot run a Newton-Raphson because the whole purpose of this talk is to understand EM. We have to be faithful to EM. It turns out if you run EM long enough, okay, and this is a very small step, right? Very small step. If you run long enough, an EM algorithm is kind of mimicking and one step Newton-Raphson, and that's the way we show that. Okay, it's not only rate optimal but also attaining the right constant. So and that's a high level of proof, and here is the rigorous proof. The rigorous proof is this. Okay, we have the output, the t plus 1 step, which is equal to the output from the tth iteration, then plus the gradient descent, right? Then subtract MLE. Subtract MLE, I'll have another actual term. What's that? That's just 0, right? And then the next step, okay, I just do Taylor expansion. Okay, very simple Taylor expansion. And then you have a matrix over here. It turns out you could show that the spectral norm of this matrix is bounded by 1. And then you have contraction. It turns out it's very interesting over here. Okay, and with very high probability, and this guy, the spectral norm of this guy is bounded by 1. It turns out on that event, an EM converges to MLE pointwise. So, and of course, you do not need to run forever. And actually, you could show that as long as you run square root of n times log n steps is enough in the third stage. Okay, so that's the proof. And in summary, and we have 3 stages. The most complicated one is the first stage, and a very important idea is the sum perturbation. And to me, the most interesting one, and one of the most interesting thing is the asymptotic efficiency. And the second step is more or less routine, but not trivial. Okay, so this is the last slide, and as I commented, it's a very simple model. It's a useless model, and I hope this would be the first step, and toward understanding EM, and for more complicated models, and for example, Gaussian mixture with K components, or even more complicated models. And in deep learning, I know, and a lot of people are fascinated by GAN, and GAN is even more complicated algorithm, right? A gradient descent and gradient ascent, and you alternate. That's even harder. And can we really do something over there? Thank you.